Have you ever just paused your typing for a split second and boom, a perfectly formatted chunk of code magically appears right there in your editor? Well, you've witnessed a modern engineering marvel. Welcome to this explainer, where we are going totally under the hood to demystify the complex machine learning system design that powers AI coding assistants like GitHub Copilot and Cursor. We are going to tear down the architecture and see exactly how that magic happens. So, here's a fascinating question to kick us off. When you're using an AI coding assistant, do you think you're interacting with a single AI entity? Just one brain? Actually, assuming there's just a single set of constraints is a total engineering rookie mistake. What's really happening is a beautifully orchestrated illusion. Okay, before we start drawing boxes and lines for the architecture, we need to nail down our ultimate goal. What are we actually trying to achieve? The core objective isn't just to generate text. It is about genuinely boosting your productivity. But there is a massive catch. We have to pull this off without introducing bugs, without creating nasty security vulnerabilities, and definitely without violating any open source licenses. Absolute code safety is totally non-negotiable here. Here is our agenda for today. 1. The goal. 2. A tale of two systems. 3. The secret sauce of context. 4. Architecture and online serving. And 5. Evaluation, safety, and privacy. Let's dive in. Section 1. The goal. Building the ultimate assistant. Right, let's get into it. We are basically juggling two massive expectations at once. On one hand, we need ultra-low latency, context-aware completions that pop up instantly. On the other hand, we need this deep, repo-grounded chat that completely understands your whole code base. And all of this has to be wrapped up in strict security and licensing safeguards. It's this monumental balancing act between speed, intelligence, and safety. Section 2. A tale of two systems. Latency versus capability. Here is a super interesting insider interview tip. Designing these systems with just one set of constraints is a trap a lot of people fall into. You absolutely cannot build a world-class copilot if you treat the instant autocomplete and the sidebar chat as the exact same engineering problem. They are, fundamentally, two totally different products operating right under the same roof. Think about it like this. Inline completion is an ultra-fast latency game. We're talking a P95 latency of under 400 milliseconds. To hit that, you rely on small, highly distilled fill-in-the-middle, or FIM models. It has got to be lightning fast. But when we switch gears over to chat or agent mode, we can slow down. This is a deliberate, multi-file capability game. You can afford seconds of latency here because you're leveraging massive models and complex retrieval augmented generation across your entire repository. So it's raw speed versus deep thought. Section 3. The secret sauce. Context. What beats complex embeddings? The absolute biggest quality lever we have isn't just throwing a larger, more expensive model at the problem. Nope, it is context selection under a wildly tight token budget. Imagine you only have a few thousand tokens to work with. It's kind of like packing a tiny suitcase for a month-long trip. Deciding exactly what code snippets to show the AI is literally the make or break engineering decision. So, we have to meticulously assemble this context. We pull from your immediate local context, like the code right before and after your cursor. We grab repo retrieval for related files. We look at the abstract syntax tree for accurate API signatures, and even project configs like your linting rules so the AI writes code in your exact style. But take a look at that third bullet point, recency. Believe it or not, knowing what file you were looking at 10 seconds ago frequently completely crushes complex, heavy mathematical embedding similarities when it comes to predicting what you're going to type next. Smart heuristics, like recently edited files or tabs you just had open, are honestly the strongest indicators of what a developer actually intends to do. Section 4. Architecture and online serving. The life of a request. Let's trace how this all comes together in milliseconds. Imagine you just type a single bracket. Bam! Step 1, the IDE debounces the keystroke and gathers that local context. Step 2, the context assembler frantically retrieves repo snippets. Step 3, rapid generation via the FIM model. Step 4, instant post-processing for security. All of this is happening before that little gray ghost text ever even appears on your screen. Zooming out for a second, just look at the massive orchestration required here. You've got the live, ultra-fast online serving path up top connecting your IDE to the LLM. But then, look down at the bottom half. That's the offline indexing path. Repositories are constantly being parsed, symbols extracted, and embeddings generated in the background. This ensures the online system always has fresh data to pull from instantly. Sitting right at the intersection of these offline and online worlds is the context assembler. Think of this module as the critical traffic cop of the whole operation. It's constantly pulling fresh data from the offline index and packaging it perfectly into the prompt for the code LLM, all while the clock is relentlessly ticking down on our strict latency budget. Section 5. Evaluation, Safety, and Privacy. Measuring True Value. Now, this brings us to a major system design trap. When you are evaluating an AI coding assistant, optimizing solely for the acceptance rate, meaning how often a developer hits tab to accept the code, is highly misleading. Honestly, developers will mindlessly accept super short, obvious completions like closing brackets or single variables all day long. So while acceptance rate is easily gameable, the true metric of value is retention. We need to track whether the AI-generated code actually survives in the codebase after your subsequent downstream edits, and if it ultimately passes your unit tests. If you accept it but delete it 5 seconds later, well, the AI failed. Retention is the absolute gold standard for measuring real developer productivity. Furthermore, if you want enterprise adoption, it hinges completely on trust and strict privacy. Proprietary enterprise code must be isolated per tenant. Under literally no circumstances can customer A's code leak into customer B's completions. That means you absolutely cannot use tenant code to train shared models without explicit opt-in consent. To guarantee this safety, the system is relentlessly running quality checks in the post-processing phase. Right before showing you a completion, it scrubs for secrets, removes personally identifiable information, uses similarity filters to block the exact regurgitation of strictly licensed code, and even scans against databases of known vulnerabilities. It's this massive, invisible safety shield working for you on every keystroke. This architecture is already wildly sophisticated, but honestly, we are just at the beginning. As we move from simple, low-latency autocomplete toward advanced autonomous agents that can loop through multi-file edits, run their own unit tests, and basically self-correct until the build goes green, we have to ask a pretty profound question. In a few years, how much of the coding process will remain purely human? Thanks for joining me on this deep dive into the system design magic of AI copilots. Keep learning, and I'll catch you in the next explainer.